Welcome to our tutorial on land use and land cover classification using QGIS and Landsat 8 imagery. Whether you're a GIS enthusiast, an environmental scientist, or just curious about mapping the Earth's surface, you're in the right place. In this video, we'll guide you step by step on how to transform raw satellite data into meaningful land use insights. To access and download Landsat 8 to 9 satellite imagery using Earth Explorer, you'll need an account. Once you've signed up, log in to begin. Now, let's set up our search criteria. On the left sidebar, select Address Ja Place as the geocoding method. In the input field, type your region of interest. In this case, it is Seoul, South Korea, and click Show. A list of coordinates will be displayed. Select the one that matches your area of interest. Verify the location on the map to ensure it's correct. Once the location is verified, it's time to specify the date range. Scroll down to the Date Range panel and set the start date to January 1st, 2024, and the end date to December 9th, 2024. Next, adjust the cloud cover settings. Scroll further down and set the range to 0 to 10%. This ensures we only retrieve images with minimal cloud coverage. When you're satisfied with these settings, click on the Datasets tab to proceed. Under the Landsat category, expand Landsat Collection to Level 1 and check the box for Landsat 8-9. This will filter your results to include imagery from these satellites. With everything set, click the Results button to search for datasets matching your criteria. Here, you'll see a list of available datasets, including details like acquisition date, cloud cover, and scene ID. Review the list and choose the dataset you want to download. You can click the footprint icon to visualize the exact polygon of interest on the map. This helps confirm that the dataset covers your desired area. Once you've selected your dataset, click Download Options. Under Product Options, download the following files: bands 1 to 7 for the imagery data and the MTL file in both TXT and XML formats. These are essential for atmospheric correction. That's it. You've successfully accessed and downloaded Landsat 8 to 9 imagery. Remember to organize your files for easy access. Let's dive right in. First, open your QGIS application. Once it's open, you'll see the main interface, which is ready for us to start. Now, click on the Project menu in the top navigation bar. Select New to create a fresh project. Save this project in a folder named Seoul. We'll name the project file Seoul Map to represent the Landsat imagery we'll be using. Next, let's add the Landsat raster layers. Go to the Layer menu at the top. From here, select Add Layer and then Add Raster Layer. A floating raster window will pop up. Click the three-dot button to browse your files. Find the Landsat images of Seoul saved on your computer, select them, and click Add. Once the images are loaded, click Close. To keep things neat, you can minimize the loaded layers in the Layers panel. Just click the small arrows next to the layer names. Now, it's time to pre-process the images. Click on the SCP menu, that's the Semi-Automatic Classification plugin, and select Pre-processing, then Image Conversion. In the SCP pre-processing window, click the yellow folder button labeled Directory containing bands. Navigate to the folder containing your Landsat bands and select it. Make sure to check the box for Apply DOS 1 Atmospheric Correction. Once ready, click Run. When prompted, choose the same folder directory for the output. This process may take some time, so wait patiently. You'll hear a notification sound once it's completed. After pre-processing, let's add the new layers to our project. Go back to the Layer menu, select Add Layer, and then Add Raster Layer. In the floating raster window, upload all the new layers we just created. Click Add to load them into your project. Once the new layers are added, minimize them in the Layers panel for clarity. Then, find the older, unprocessed layers. Right-click on those layers and select Remove Layer to clean up your workspace. After deleting the previously loaded band layers from your Layers panel. Now, let's rearrange the band layers in ascending order to prepare for stacking. Ensure the bands are arranged in ascending order from Band 1 to Band 7. With this done, let's move to the SCP panel. Under SCP, click Band Set, and the SCP panel will appear on the interface. In the SCP panel, click the plus icon to add the band layers. A mini panel will appear, allowing you to select all the band layers. After selecting them, click OK. Next, let's set the band quick settings. Select Landsat 8 OLI for the wavelength and set the wavelength unit to or micrometers. This step ensures the correct spectral settings for your bands. Check the boxes for Create Virtual Raster of Bandset and Create Raster of Bandset, stack bands. Now, click Run to start the process. Select an appropriate folder to save your output file. After you hear the confirmation sound, your band stack is ready. Once the process is complete, import the raster layer you just saved. Select the stack raster file, and your map image will load onto QGIS. To create a true color composite, go to the Layer Properties of your stack raster file. Set Band 4 for the red band, Band 3 for the green band, and Band 2 for the blue band. Click Apply, and your true color composite will be displayed. Next, go to the SCP dock and click the Training Input bar. Create a new training input, name your training file, and save it in your desired folder. Finally, go back to the layer properties of your stack raster file. Set Band 5 for the red band, Band 4 for the green band, and Band 3 for the blue band. Click Apply, and a false color composite will appear. This makes features that are otherwise difficult to see more visible for our training input. For collecting forest data, first is to set both MCID and CID into one, and assign the class ID and name to Forest. Then, simply zoom into areas with forest vegetation, then use the Polygon tool to draw training polygons over areas with forest. Repeat this technique until you've collected enough samples. Ensure that they are evenly scattered across the image. Then change the color of all forest data to green for easier recognition. For collecting urban data, set both MCID and CID into two. Assign the class ID and name to Urban. Then zoom into areas that well-define urban zones like city centers, industrial complexes, or residential neighborhoods. Again, use the Polygon tool to draw training polygons over the urban areas. Collect at least enough samples. Then change the color of all urban data to any particular color you like. For this video, we chose pink for easier recognition. For collecting water data, set both MCID and CID into 3, assign the class ID and name to Water. Use the same tool as instructed before to collect training data for water. If you want to clearly identify where water bodies resides, such as rivers or lakes, return to the false color composite to easily identify them. After collecting enough samples for water, change the color into blue for easier recognition. Now, click on the SCP menu in the top navigation bar. Choose the band Processing, then Classification. Make sure that you selected Maximum Likelihood, then click Run. Save the file name as Maximum Likelihood Map. Again, click on the SCP menu in the top navigation bar. Choose the band Processing, then Classification. And now, choose Minimum Distance. Then click Run. Save the file as Minimum Distance Map. For spectral angle mapping, follow the same process. Click on SCP menu, Band Processing, Classification, and click Spectral Angle Mapping, then click Run, and save as Spectral Angle Map. To ensure the quality of our land cover classification, we need to perform an accuracy assessment. First, we create a validation dataset. In the Semi-Automatic Classification plugin dock, we click Create New Training Input and label it Validation. Using a false color composite image, we collect validation data for each class: forest, urban, and water. It's important to have a sufficient number of samples per class, calculated as the number of bands plus 1. Since we're using only 7 bands from Landsat 8, we need to have 8 samples per class. We'll use green to represent forest, which is the Class 1, pink for urban areas, Class 2, and blue for water, Class 3. Once our validation dataset is ready, we can move on to the accuracy assessment. We open the Semi-Automatic Classification plugin and go to the Post-Processing tab, then select Accuracy. We'll assess each classification method individually, starting with maximum likelihood. We load the maximum likelihood map as the classification to assess, then our validation dataset as our reference raster. We also need to select the appropriate vector field, which in this case is the macro field. Then we click Run and save the file as maximum likelihood accuracy. The result: an impressive overall accuracy of approximately 99.26%. Next, we repeat the process for the minimum distance classification. This method achieves an overall accuracy of 97.83%. Finally, we assess the spectral angle classification, which yields an overall accuracy of 98.64%. Now, let's analyze the accuracy assessment results of our land use and land cover classification of Seoul, South Korea. We'll start with the maximum likelihood classification. The overall accuracy is an impressive 99.26%, indicating a highly successful classification. We begin with the error matrix. This matrix shows how well the classified map matches the reference data pixel by pixel. 18,293 pixels were correctly classified as Class 1. 9,090 pixels were correctly classified as Class 2. And 2,571 pixels were correctly classified as Class 3. The other numbers show where the classification got confused. For example, 18 pixels that were actually Class 1 were incorrectly classified as Class 2. Ideally, we want high numbers along the diagonal, correct matches, and low numbers everywhere else, mismatches. As you can see, the vast majority of the pixels fall along that diagonal, indicating a high level of accuracy. This matrix illustrates the pixel-by-pixel agreement between the classified map and the reference data. The area-based matrix provides a more proportional view of the accuracy, along with confidence values, including the standard error. Class 1 has a producer's accuracy of 98.9078% and a user's accuracy of 99.9017%, with a very low standard error of 0.0005, indicating high accuracy and reliability. Similarly, Class 2 shows a producer's accuracy of 99.7695% and a user's accuracy of 97.8261%, also with a low standard error of 0.0005. Class 3 stands out with a perfect producer's accuracy of 100% and a user's accuracy of 99.8834%, with an even lower standard error of 0.0001. These low standard errors across all classes further reinforce the high accuracy of this classification. Class 3 stands out with perfect producer's accuracy. Every pixel truly belonging to this class was correctly identified. Overall, this maximum likelihood classification demonstrates exceptional accuracy and reliability for mapping land cover in Seoul. Let's move on to the next and delve into the accuracy assessment results for the minimum distance classification, presented in this table. The overall accuracy is 97.8328%, which, while still commendable, is slightly lower than the maximum likelihood classification. For the error matrix, the numbers along the diagonal represent correctly classified pixels. 18,313 pixels were correctly classified as Class 1. 8,639 pixels were correctly classified as Class 2, and 2,571 pixels were correctly classified as Class 3. There are 128 pixels that actually belong to Class 1 were incorrectly classified as Class 2. While there are more misclassifications compared to the maximum likelihood results, the strong diagonal pattern still suggests good agreement. Class 1 boasts a producer's accuracy of 99.016% and a user's accuracy of 99.032%, with a standard error of 0.0003. Class 2 has a producer's accuracy of 94.8194% and a user's accuracy of 98.54%, with a standard error of 0.0007. Class 3 has perfect producer's accuracy, 100%, and a user's accuracy of 88.1083%, with a standard error of 0.0008. Interestingly, despite the slightly lower overall accuracy, Class 3 in the minimum distance classification shows a higher user's accuracy, 88.1083%, compared to the maximum likelihood result, around 80%, as seen previously. This means that when the minimum distance classifier assigns a pixel to Class 3, it's more likely to be correct. Overall, while the minimum distance classification has a slightly lower overall accuracy than maximum likelihood, it still demonstrates very good performance, with particularly strong results for Class 3, as evidenced by the high user's accuracy and low standard error. Lastly, let's move on to our final classification method and examine the accuracy assessment results for the spectral angle classification. This method takes a different approach to classifying pixels, and it will be interesting to see how it compares to the previous two. Looking at the table, the overall accuracy for the spectral angle classification is 98.6413%. This puts it in between the maximum likelihood and minimum distance classifications in terms of overall performance. Once again, we'll start with the error matrix at the top. Here, we see a similar pattern to the other classifications, with the majority of pixels falling along the diagonal, representing correct classifications. 18,394 pixels were correctly classified as Class 1. 8,802 pixels were correctly classified as Class 2, and 2,571 pixels were correctly classified as Class 3. There are some misclassifications, of course. For example, 278 pixels that actually belong to Class 1 were incorrectly classified as Class 2. However, the overall picture still points to a high level of agreement between the classified map and the reference data. Moving on to the area-based matrix, we can see the producers' and users' accuracies for each class, along with their standard errors. Class 1 has a producer's accuracy of 99.4539% and a user's accuracy of 98.5111%, with a standard error of 0.0006. Class 2 has a producer's accuracy of 96.6085% and a user's accuracy of 98.8656%, with a standard error of 0.0007. And Class 3, once again, shows perfect producer's accuracy 100% and a user's accuracy of 98.8086%, with a standard error of 0.0002. It's interesting to note that while the spectral angle classification doesn't quite reach the overall accuracy of the maximum likelihood method, it does show slightly better performance for Class 2 compared to minimum distance, with a higher producer's accuracy and a lower standard error. Overall, the spectral angle classification provides a solid and reliable option for land cover mapping, demonstrating high accuracy across all classes and a good balance between the strengths of the maximum likelihood and minimum distance methods. In conclusion, all three classification methods demonstrate high accuracy for mapping land cover in Seoul. The maximum likelihood method boasts the highest overall accuracy, while minimum distance excels in classifying Class 3, and spectral angle shows a good balance between the two. And there you have it. From raw pixels to actionable insights, we've explored the transformative power of geospatial data analysis, diving deep into the accuracy assessment of land use and land cover classification in QGIS. In the vast universe of data, a map is more than just lines and points. It's a canvas of stories, connections, and possibilities where precision shapes understanding. So, stay curious, keep exploring, and continue charting the secrets hidden within the where. Because at the heart of every map, ours is making decisions that matter,